Hi everyone, welcome to Phys 3500, Classical Mechanics. I'm your instructor, Dr. TJ Hammond. This week we'll be covering Chapter 6, Calculus of Variations. This is the lecture for Monday, September 21st. So why are we covering Calculus of Variations? So up to now, classical mechanics has always been formulated by Newton's laws. So this is what you guys are familiar with seeing and understanding dynamics and interaction of particles. So momentum is, you change momentum by applying some force. So by Newton 2, you have F equals ma, or more precisely, F is the rate of change of the momentum. However, this isn't the only way of thinking about it, and in fact, as soon as Newton had devised his equations of motion, he had already started to think about these calculus of variations, and his contemporary Leibniz had actually, who was a rival of Newton, had hated how Newton formulated his mechanics and was looking at a different way of approaching this. And he wanted to look at it in terms of scalars. So Newton had formulated this in terms of forces and momenta, but forces and momenta are all vectors. So everything is complicated because you have to describe everything in terms of x, y, and z in Cartesian coordinates, or r, theta, and phi in spherical coordinates, or something like that. And that becomes quite complicated. So instead of doing it that way, Leibniz has started to think about these in terms of scalars. And so a scalar that you're familiar with is energy. So instead of thinking about this in terms of forces, they were thinking about this in terms of potentials. Now, it's more difficult to formulate, which is why it didn't happen before Newton. It actually took about 100 years or so, or even 150 years, and many very, very skilled mathematicians and physicists to come up with how the formulation for Lagrangian and Hamiltonian mechanics. But we'll see over the next few weeks how useful they can actually be. So as I said, they, instead of using forces and momenta, they show that energies act on particles and they can dictate the particle trajectories. So this week we'll only cover the calculus of variations, and that's because it's likely new math for you. There isn't really that much physics in this week. It's to introduce the mathematical concepts so that we can then spend the next several weeks developing the Lagrangian and Hamiltonian mechanics. So the daily assignment that's due Wednesday, read and summarize section 6.1 and 6.2, which is basically what we'll be covering in this lecture. So really what I want you to do is read the notes that I post on Blackboard, listen to this video, come to class, and then read the textbook, and it'll all be basically the same material, and hopefully then you'll understand how this material, how it works. Okay, so introduction to calculus of variations. So Newtonian mechanics have worked for us so far. As I said, for intermediate mechanics, everything you saw in first year, intermediate mechanics, and the review of stuff that we've seen so far are all based on Newton's laws. But some problems are actually quite difficult to solve this way, and we'll get into some problems that are basically not possible to solve using Newtonian mechanics, but they're actually quite straightforward to set up with Lagrangian equations of motion. But the thing is that we need to develop some of this new language as mathematical tools to be able to do this. So that's what we're going to be doing this week. So we call this the calculus of variations. What does that even mean? And so what we want to do is find some function y of x such that this integral j, which is from position x1 to a final position x2 over some function, and this function is a function of y of x and also the first derivative of y of x with some independent variable x integrating over x. What we want to do is find some extremum of this value. So we don't know what any of these terms are yet, but just in general, we have some independent variable x. So this could be some position. Often it'll be time when we actually get to mechanics, but for now we'll just say it's some position, some independent variable. And then we also have these dependent variables, x, or y of x and y prime of x. where y prime of x is the full derivative of y of x. And j is called a functional, which is a function of a function. So it's this functional that we want to understand, that we want to take the extremum of. So when we say it's an extremum, it means we either have a maximum or a minimum. So if you think of a normal function that we might plot, so if we have some function, we'll call this as a function of t, and we'll call this our function h of t. We could have this thing going like that. And so what we want to do is find this position where it's a minimum. And it'll be this independent variable where it can be t or x or whatever. So we have this functional j, and what we want to do is vary y of x until we're at some extreme value of j. And as I said, it'll typically be a minimum for these physical problems. In principle, mathematically, it just needs to be an extremum, but really what we'll be seeing, especially for this course, is that these will be a minimum. So in general, let's assume that we have some function of the form y of x is actually some function of alpha and x, where we have this term y of 0x plus alpha eta of x. So this function y of 0 and x is the function that yields the extremum for j. We don't know what y of 0 and x is yet. We don't know what j is either, but we know that this is going to be the thing that yields the extremum for it. So any value of alpha will lead to this function that doesn't minimize or maximize j. This eta function, eta of x, has to go to 0 at x1 and x2 because we know the starting point and the ending point. So we know what x1 and x2 are, so we have x1, for example, and this follows some path to x2 up here. We don't know what this function is here, but we know that y of 0 and x is the function that that makes an extremum for j. Okay, so eta is anything that starts off at x1 and ends at x2, but it can go in any possible path. Also, because it's the only thing that we really, the constraint that we put on this function, eta, is that because we're going to be taking the derivatives, we need this function to be continuous and differentiable. So putting this together with our definition above, we have j as a function of alpha is going to be this integral from x1 to x2 of this function, which is now y of function of alpha and x, and y prime of function of alpha and x, still with the independent variable x and integrating over x. So that means that we get the extremum when we take the derivative of j, this functional, with respect to alpha, when alpha is equal to 0, gives us 0. This seems very abstract. It's true, but we'll get to an example soon enough. So this is our example. As I said, this is quite abstract. This is one of the reasons why we don't teach this until third year. If it were simpler than Newtonian mechanics, we obviously would have taught it earlier. It turns out to be a very general and robust tool to solve these dynamical problems and set up these equations of motion, but it is quite abstract, requires some complicated calculus, so that's why we wait till third year. Okay, so for this example, consider some function f, which is equal to dy by dx all squared, where y of x is equal to x, so it's just a straight line. So of course we have this y of x is equal to x right here. Now, what we want to do is add this eta function, and we're going to say it has to satisfy these conditions. It has to be at x1, which is over here, and x2, which is over here. that it has to be equal to the same thing. So that eta function has to be 0. So we'll say this function is going to be sine x. And this is just a simple example. And oh, this should obviously be 2 pi. Show that the stationary value of j alpha occurs when alpha is equal to 0. Okay. So y of alpha x is equal to x plus alpha sine x. All right. So d by dx of y alpha x is equal to 1 plus alpha cos x. So what we said is our function is dy by dx squared. So what we get is f is equal to 1 plus alpha cos x squared is of course 1 plus 2 alpha cos x plus alpha squared cos squared x. So then our functional j of alpha is equal to the integral from 0 to 2 pi of 1 plus 2 alpha cos alpha plus alpha squared cos squared x dx. But of course, we get 1 integral of 1 from 0 to 2 pi is 2 pi. Oops, I noticed a mistake here. This should be cos x. And this should be cos x. And the integral of cosine x is going to be sine x, but sine x at 0 is 0, and sine x at 2 pi is again 0. So then we get alpha squared, and then we get cosine squared. The integral of cosine squared x just gives us pi. Okay, so when is this an extremum? So j of alpha is equal to 2 pi plus alpha squared pi dj by di alpha is going to be equal to 2 alpha pi. And we want this equal to 0, tells us alpha is equal to 0. So what this is telling us is that this equation, seems like I've lost the screen. Eventually they'll come back to us, I assume. So what this is telling us is that y of x equals x is the shortest possible path from x1 to x2, which we already knew, but this is just using this as a simple example to understand this fact. Okay. Now, what does this mean? So it is necessary for j to have an extremum, but what is this partial derivative of j with respect to alpha evaluated at alpha equals 0 mean? So let's explicitly go through this. We have that this derivative of this functional j with respect to alpha means that we're taking the derivative of this integral with respect to alpha. And so, but we have this function of y, which is also a function of x. And so we have to take the derivative of f with respect to y, which is the partial derivative of y with respect to alpha, or sorry, multiplied by that. Plus we have the derivative of f with respect to y prime times the derivative of y prime with respect to alpha. And so what we get then is, since we said before that y is a function of alpha and x, where this y0 of x plus alpha eta x is our function, then if we explicitly take that and note that d by dx of y is this y prime, then of course we have this partial derivative of y with respect to alpha is of course going to be equal to eta, but we have this dy by dx is going to give us alpha and x is going to give us dy0x by dx plus alpha d eta by dx. Right? So what that means then is then when we take the partial derivative of that with respect to alpha, since there's no alpha term here, this will be 0. And so what we get is dy prime by d alpha is equal to d by dx of eta x. Okay? So we can put that in, and we can substitute that in here for eta, and we can substitute this in here for d eta by dx. Now we can also do some integration by parts to get the second term to 2 terms, but it turns out that one of them will just be equal to 0. And so then, since the endpoints have to be 0, so then this means that when we substitute this in, what we get is the partial derivative of j, this functional with respect to alpha, is going to be this partial derivative, the integral from x1 to x2 of this partial derivative of f. My screen seems to have gone again. This partial derivative with respect to of f with respect to y minus the full derivative of f, the partial derivative of f with respect to y prime with respect to x times eta x dx. Okay, but the thing is that remember this has to be an extremum, or j has to be an extremum, so that means that this has to be equal to 0. So that means that for this in general to be equal to 0, this part inside the integral needs to be equal to 0 for this to be true in general. Okay. So Euler's equation is this. Is just this statement. Is we're saying that the stuff inside that integral is equal to 0. So the thing that's nice about this is that although we had this functional j and we didn't know what this complicated function was, it turns out we never need to know what that is, because we know that everything inside the integral has to be equal to 0, and so we can just set all that stuff inside the integral equal to 0. And so this is the Euler's equation in the first form. It's the necessary condition for j to have an extremum. And that was what we posited at the beginning, is that what we wanted is this functional to have some extremum, or the derivative of this functional with respect to this parameter alpha to be equal to 0. So we don't actually need to solve for j. We don't need to solve this complicated integral. We can just take the derivatives of these functions and set that equal to 0. And that tells us that j has to have an extremum. And that is Euler's equation. So that's it for Monday's lecture. We'll be doing some more examples on Euler's equation on Wednesday.